Hey everyone, welcome. Think of me as your enthusiastic big brother in chemistry, because today we are going to crack the code on literally one of the most notoriously confusing topics out there. This explainer is going to completely demystify the D and F block elements. We're breaking down the source material to reveal the beautiful, elegant logic that's been hiding right in front of us the whole time. Okay, let's just dive right into this. So if you've ever studied inorganic chemistry, you probably share this universal frustration, right? It feels like you learn a solid rule, and then bam! Immediately, you're hit with three completely random exceptions to memorize. It's the ultimate fear for any student. Just endless, frustrating memorization. Honestly, it can make you feel like you're just banging your head against a brick wall. But here is the empowering truth, and it's exactly what we're going to prove today. There are no exceptions. None. Zero. There are only hidden rules that, well, you just haven't been introduced to yet. Once you see the underlying logic, all that chaos completely disappears. Everything happens for a reason, and today, we're going to find out exactly what those reasons are. Here's our master plan for this explainer. First, the electron's address, then the building without lifts, followed by the D-block bridge, the logic behind exceptions, and finally, the lanthanoid contraction mystery. All right, kicking things off with Section 1, the electron's exact address. To really understand the elements, we've got to first understand the electrons inside them. And finding an electron? Well, it's actually a lot like trying to find a friend in a massive, sprawling city. You don't just guess where they are, right? You narrow it down. Step 1, you find their city. In chemistry, that's the main shell, represented by the letter N. Step 2, you zoom into their specific neighborhood or colony. That's the subshell, like S, P, D, or F. And finally, Step 3, you literally knock on the door of their actual house. And that's the orbital. This is the spot where the probability of finding your electron is the absolute highest. It's literally an exact address system. Moving right along to Section 2, the building without lifts. Okay, so now that we have the address system down, how do electrons actually choose which house to live in? I want you to imagine an enormous, completely empty apartment building, but it has absolutely no elevators. Electrons are exactly like lazy tenants. The Aufbau principle tells us they will always fill the bottom floors, the lowest energy levels, first, because, well, no one wants to climb the stairs if they don't absolutely have to. Then we have Hund's rule. Imagine arriving at a multi-room apartment with a bunch of strangers. You're going to grab an empty room all to yourself first, right? Well, electrons do the exact same thing. They occupy empty orbitals in a subshell one by one before they ever agree to pair up and share a space. Now, here's the secret to ultimate chemical stability. It all comes down to symmetry. You see, electrons are constantly moving around and exchanging places with each other. If a subshell is perfectly half-filled or perfectly fully filled, it creates perfect symmetry. This lets the electrons exchange places way more frequently without messing up the overall structure. And more exchanges mean they release more energy. In the chemistry world, losing energy means gaining massive stability. This is a really huge aha moment for understanding everything else we're going to talk about. Which brings us to Section 3. The D-block transition bridge. Armed with those ground rules, let's zoom out and look at the periodic table. Right smack in the middle, you have the D-block. It acts as this crucial bridge connecting the highly electropositive elements on the far left, the ones that just love giving away electrons, to the highly electronegative elements on the right that love stealing them. We usually call these the transition elements, but the strict definition of that word is absolutely key here. To be a true transition element, an atom absolutely must have a partially filled d orbital in its ground or ionic state. Basically, there has to be unpaired electrons just hanging out in that d subshell. Take scandium, for example. It's got a configuration of 4s2, 3d1. That one lonely electron in the d orbital means it is partially filled, making scandium a true bona fide transition metal. But look at zinc all the way at the end of the row, 4s2, 3d10. Its d orbital is completely packed to the brim with 10 electrons. There are 0 unpaired electrons. Because of this, zinc isn't technically a transition metal at all. It's just a pseudo-transition element. All right, let's get into Section 4, the logic behind exceptions. It is time to put on our detective hats. We're going to tackle the most notorious terrors of the D-block, the ones that honestly give students nightmares: chromium and copper. If we just follow those building without lifts rules we just established, these two seem to blatantly ignore them. They are your classic textbook exceptions. But remember what we said at the very start? There are no exceptions. So why do they seem to jump the rules? Well, here is the massive revelation. Look at chromium's expected setup, 4s2, 3d4. Do you see it?
It is just one single electron away from being a perfectly half-filled, highly stable 3d5. Because the energy gap between the 4s and 3d floors is incredibly small, an electron literally just jumps ship from the s to the d orbital. It sacrifices having a full s orbital just to achieve that unshakable half-filled stability in the d orbital. And copper? It does the exact same thing to reach a fully filled 3d10. So you see, it's not an exception at all. It's a brilliant survival strategy for maximum stability.
Because this entire 3D series from scandium to zinc is so incredibly vital, let me give you a really fun, catchy little tool to instantly memorize it. Just remember this phrase from the source material: Sky TV Coropati me feco nico gite. It's a quick memory hook that perfectly lines up scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Keep that in your back pocket. It's a real game changer.
Now, let's connect all these micro-quantum rules to the macro world that you can actually touch. Ever wonder why transition metals are so physically hard? It all comes down to metallic bonding. Remember those lonely, unpaired d electrons we talked about? Well, they actually jump out and act as a highly conductive glue that holds the metal atoms together. Simply put, the more unpaired electrons you have, the stronger the metallic glue becomes and the harder the metal is, which means a much higher melting point. This rule of unpaired electrons acting like a glue perfectly explains why melting points shoot straight up as we move from scandium to chromium. But then, right in the middle, at manganese, the melting point suddenly just crashes down before spiking right back up for iron. So why this bizarre dip? Time to go back into detective mode.
The answer lies right in manganese's electronic address, 3d5. It has exactly 5 unpaired electrons, making it perfectly, symmetrically half-filled. And what do we know about perfectly half-filled orbitals? They are immensely stable. Manganese is so incredibly happy and stable all by itself that it flat out refuses to share its electrons to act as that metallic glue. Because it won't bond strongly with its neighbors, the metal ends up surprisingly soft, and the melting point absolutely plummets. Bam! The mystery is solved by the rule of half-filled stability. Finally, we arrive at section 5, the lanthanoid contraction mystery. Let's move to our final boss-level mystery of the explainer, which is all about atomic sizes as we travel down the periodic table. And prepare to have your mind slightly blown here. Normally, as you go down the periodic table, you're adding a whole new shell, like adding a whole new ring around the city. So going from the 3D series to the 4D series, the atoms predictably get bigger. But the huge shock comes when you go from the 4D series to the 5D series. You add another entire shell, and yet, the atoms basically stay the exact same size. No way, right? How in the world can you add a whole layer to an onion and not have the onion get bigger?
Well, here is the culprit. Right before we fill the 5d orbital, we have to fill this massive, sprawling orbital called 4f. And this 4f orbital is so huge and so diffuse that it is absolutely terrible at what we call shielding. It completely fails to block the positive magnetic pole of the nucleus. Because the nucleus's inward pole basically leaks right through that flimsy 4f shield, it violently yanks the outer shell inward. And this inward pole perfectly cancels out the added size of the new shell. In chemistry, this phenomenon is known as the lanthanoid contraction. The real-world result of this contraction is honestly mind-bending. Zirconium, which is up in the 4D row, and hafnium, which is right below it in the 5D row, end up having virtually identical physical sizes. Despite being in completely different rows, they are essentially identical twins in size and chemical behavior. And it is all because of that hidden rule of pore shielding. So, we've tracked the electron's address, watched them jump ship for stability, and seen how a flimsy shield can literally shrink an entire atom. You now know for a fact that these aren't exceptions at all. They are beautiful, elegant rules governing the universe. So it kind of makes you wonder, what other scientific exceptions out there in the world are actually just elegant hidden rules, simply waiting for you to discover them? Keep questioning, keep learning, and I'll catch you on the next explainer.